All right. So, next section. This is going to be 7.3. So for 7.3, we're going to be going over the properties of Laplace transforms, and this will allow us to build up the rest of the table like what I've been promising. You can see I'm driving to work right now. I haven't actually been to my office since before the spring break and before the quarantine. I would prefer not to go out at all, but unfortunately I left all the student papers there, so if I'm going to get grading, I have to go back and get it. So I apologize if I haven't gotten any of the grades up for those of you who are actually in my class, but I'll get an exam 2 graded in the next week. In any case, yeah, so we're going to be doing work with the Posche Transform and looking at special properties. And one of the special properties is immediately apparent if you just think about taking a derivative. So if you take the derivative with respect to s, what you end up doing is you take the derivative underneath the integral. You sort of pass it through. Now, professional mathematicians would squirm and worry about whether or not you can do that, but you see a lot of people doing this, and there's a lot of requirements that a lot of these transforms actually meet that we're allowed to actually do that moving exchange between integral and derivative. I won't go over to particular requirements here, but this generally can be done, and you're usually safe. It is also known as the Feynman trick because it got popularized in Richard Feynman's book, Surely You Must Be Joking, Mr. Feynman, and he talked about it there. So when you take the derivative of the Laplace transform and you move it to the inside, you'll notice that you're taking the derivative with respect to s, and there's only one function that has any dependence on s itself, and that is e to the minus st, which means all you're going to do is you're going to pop out a minus t out of the derivative. So we can use that to our advantage in a lot of cases. So for instance, we know the Laplace transform of 1 is just 1 over s, and now when we take the derivative, well, we know the derivative is negative 1 over s squared, and when you take the derivative on the inside of the integral, now suddenly that negative 1 over s squared is the Laplace transform of negative t. And you can continue doing this to get t squared and t cubed and etc. until we have just built up our new table, the t to the n part of our table. There's other things you can do. So if you multiply by e to the at, then you'll notice in the Laplace transform you can actually combine e to the at with e to the minus st, and that really is just a shift, because then you just exchange a and s with a minus sign, and now you are suddenly taking a Laplace transform at s minus a. So these are all really handy tools to get at, and we'll build up our table from this. So that's where I'm going to leave it now, and we'll get back to the notes. And don't worry, I'm not going to write them while I'm driving.
All right. So today this is going to be 7.3 out of section 7.3 out of Nagle, Saff, and Snider's book. All right. So what is this going to be talking about? Well, we're talking about the properties of the Laplace transform. Okay. So what are these properties? So we have several that we're going to be talking about today. The first one is probably the most straightforward, and this is the linear property. So if I take a look at for two functions f and g, and I combine them as a f of t plus b g of t, where a and b are real numbers, then this can be written as a, say, capital F of s plus b times capital G of s. So this is linear. Now this follows just straight from the integral representation. So if I write this as the integral from, say, 0 to infinity of a of f of t plus b g of t times e to the minus st dt, Well, we can go ahead and we can distribute e to the minus st through, and we can also split that resultant sum over the integral. So this is, just skipping a few steps. This is what we end up getting. So this is stuff you're pretty used to doing intuitively in calculus, because we split integrals term by term all the time, right? So this isn't any sort of big mystery. So this is the linearity property. So how does that help us? Well, if we take something like this, so we say we take the Laplace transform of a plus e to the at, we can split this as a times the Laplace transform of 1 times s plus the Laplace transform of e to the at s, and we already know what those Laplace transforms are, so we're going to get a over s plus 1 over s minus a, right? So we just take the Laplace transform of these guys independently. Okay, so that's a nice and easy way to get started with properties, but let's take a look at one that's a little bit more interesting. This first one is called a shifting property. So if I take that e to the at and I multiply it by f of t, then what am I going to get? So all of these properties really come down to properties of integrals and also properties of the exponential function. And so what we can do is we can just go ahead and rewrite this as an integral from 0 to infinity of, say, e to the at times f of t times e to the minus st dt, right? And if I combine these two guys, then what can I do? And I'm going to factor out a minus sign as I go. So I'm going to have an integral from 0 to infinity of f of t e to the, it'd be a minus s, but I'm factoring out a minus sign, so it gets to be minus s minus a t dt. Now, if you remember the definition of the Laplace transform, integral from 0 to infinity of f of t times e to the minus st dt. So this is the Laplace transform of f at s. Then we see that now instead of s, we have s minus a. So this is actually just the Laplace transform of f evaluated at s minus a. All right, so what just happened here? So we have the Laplace transform of e to the at times f of t just turned into the Laplace transform of just f times s minus a. So we've actually already seen this. We've seen that this is true in at least one case. So if we take a look at, say, the Laplace transform of e to the at, that's really the Laplace transform of e to the at times 1, right? So what does that end up giving us? Well, we know that the Laplace transform here on the side of 1 is equal to 1 over s. And so that is just giving us a shifting, and so that's 1 over s minus a. That's exactly what we expected when we weren't thinking about the 1 there, and that's what we calculated before. And if you look elsewhere on the table, let's see, so if I want to take the Laplace transform of e to the at, we want to put this in our table, and this is in Nagle, Saff, and Snider's table of, we wrote it down in the last lecture at the very end, and this is table 7.1. One of the last pieces in there is sign of bt. If we go ahead and take the Laplace transform of that, well, we remember the Laplace transform of sine of bt is actually equal to b over s squared plus b squared. So I can go ahead and calculate e to the at times sine of bt just through shifting this guy. So this is going to give me b over s minus a squared plus b squared. Okay, so this is another entry in our table. Okay, so that's using the shifting property. Let's see what else we can find. Another neat property, and this is a property that comes through differentiation. And again, the real trick here is that we have an exponential on the inside, and that makes this next one pretty handy. So the third property is that if we take d by ds of the Laplace transform of f at s, then what we end up getting is we have minus d by ds of the Laplace transform of t f at s. What do? So we look at the integral from 0 to infinity of f of t e to the minus st dt, and we're taking the derivative with respect to s. Now, s has nothing to do with this index variable t, so we can actually try to move it inside. That was an infinity there. It's horrible handwriting. And so what do we get? So we get the integral from 0 to infinity of f of t d by ds of e to the minus st dt. Since f of t had nothing to do with s, we just moved it straight past it. Now, this exchange of integrals and derivatives is not always going to work, but and there's a lot of mathematical things you can say to make guarantees of when it works. As far as you guys are concerned, it's going to work on everything we're going to care about. But just keep in mind that if you showed this to a mathematician and you didn't say why it worked, they might throw a fit. But in any case, now we're taking a look at the derivative with respect to s of e to the minus st, and that's easy enough to do. And so that's going to end up giving us the integral from 0 to infinity of f of t times negative t times e to the minus st dt. And that's what we wanted. So if we look at it, let's say we pull out the minus sign, integral from 0 to infinity of f of t, and we pull the t out of here, and now we get e to the minus st dt. And that is exactly what we're looking for, the Laplace transform of t times f valued at s. Okay, so that's not too bad. So what does this get us? Remember how we know the Laplace transform of 1, but we'd also like to know the Laplace transform of t. We'd like to know the Laplace transform of t squared, t cubed, and we can build up from there. So for instance, the Laplace transform of 1, we just said a second ago that this is equal to 1 over s. Well, if I want the Laplace transform of t of s, well, I know that this is going to be d by ds of Laplace transform of 1 evaluated at s, and then at the cost of a minus sign. So what does that end up giving us? So it's going to be minus d by ds of 1 over s, and this is 1 over s squared. Then we can do the same process. We want to go from t to t squared, so t times t, and we're going to take a look at minus the derivative with respect to s of the Laplace transform of t of s, and this is now going to be minus the derivative with respect to s of 1 over s squared, and this ends up being 2 over s cubed. And similarly, this last one I'm going to do explicitly. I wanted to figure out the Laplace transform of t cubed, but that's just t times t squared. So that's going to be minus the derivative with respect to s of the Laplace transform of t squared. And so it's minus the derivative with respect to s of 2 over s cubed, and that's going to end up giving us, say, 3 factorial, or 2 times 3, over s to the 4th. Okay, so we can keep this going, and then we see that the Laplace transform of t to the n at s is going to be equal to n factorial divided by s to the n plus 1. And so now we have a new entry in the table. Okay, so that's great. Now let's go ahead and combine this with what we just talked about the shifting property. So if I take a look at, say, the Laplace transform of e to the at times t to the n, well, we know that this is the same as the Laplace transform of t to the n at s minus a. Well, the Laplace transform of t to the n, we just said, was n factorial over s to the n plus 1, but now instead of s, we put in s minus a. Okay, so now we have yet another entry in our table. Okay, so that's pretty good so far. So let's see, what do we have? We have the linearity property of the Laplace transform. So this is linearity. And let's see, we have the shifting property here. Well, I don't want to mark that one. We want to mark this It's a shifting property. And now we have the derivative property. Okay, now we also built up some things out of our table. We now know this guy in our table, e to the at times sine of bt. We now know t to the n, that's in our table too. And now we know e to the at times t to the n. All right, but we're missing all those cosine chunks. So how do we get those? So the next one comes in when we take a look at the Laplace transform of the derivative f prime of t at s. And what you end up getting is s times the Laplace transform of f evaluated at s minus f at 0. Okay, so this is going to, in order to do this, we need to have one little theorem, and that's this here. So I already worked it out, and this is what we have. So we basically need to put a requirement on f prime in order to make this work. And so what we're going to assume is that f prime is of exponential order alpha. Now, if you remember, that means that the absolute value of f prime at t should be less than or equal to m times e to the alpha t for some m. Okay, so this little theorem that we're making here, it basically says that if f prime is of exponential order alpha, then so is f of t. So in order to do this proof, we first suppose that f prime is of exponential order, and so that was something we were given. And then the rest of it comes out pretty straightforward. You don't have to know how to do this, it's just so we know how we can go about this problem. But we have f of t is equal to f of 0 plus the integral from 0 to t of f prime of t dt. This is just a fundamental theorem of calculus. So I can take that and I can use what's called the triangle inequality and make everything bigger. So the integral of the absolute value of f prime of t is going to be bigger than the absolute value of the otherwise, because we're getting rid of all of our negative values. And then we just make sure we add on the positive f of 0 in absolute value. So f of 0 might have been negative, for instance, and so this guarantees that we stay positive. This is called the triangle inequality. So after that, we go and replace f prime of t with this bound from e to the alpha t. And then we can actually integrate that. And so we end up getting this. So at the end of the day, we can bound this guy and this guy by some other constant other than this, e to the alpha t, and this is what we end up getting. So what we proved is that if f prime of t is of exponential order, then so is f of t. So now what I want to do is I want to use that in order to prove what we were talking about before. So what we'll say is that if f prime of t is of exponential order, alpha, then we're going to have Laplace transform of f prime of t at s is equal to s times the Laplace transform of f of t at s minus f of 0. Okay, so let's go ahead and work that out. So this is going to use integration by parts. So we got Laplace transform of f prime of t evaluated at s is equal to the integral from 0 to infinity of f prime of t e to the minus st dt. So now we're going to set dv is equal to f prime dt, and we're going to set u is equal to e to the minus st. Right, that makes v equals f, and that makes du equal to minus s e to the minus st. Okay, so let's combine these. So we get u times v, so we get f. All right, and also let's expand the limit. So we have limit n goes to infinity of, now we're going to have f of t times e to the minus st times minus s, and this is going to be evaluated at n and 0 for t, minus Oh, that minus s doesn't go in there. Sorry, that's just u, not du. So we get 0 to n minus the integral from 0 to n of minus s, and that's where this guy is, of f of t e to the minus st dt. There we go. Okay, so now let's take a look. So this thing is equal to the limit as n goes to infinity of f of n times e to the minus sn minus f at 0. And then we get plus s times the integral from 0 to n of f of t e to the minus st dt. All right, so now since we know that our f of t is actually of exponential order by this theorem, we knew that f prime of t is exponential order, so that means f is. That means that the limit as n goes to infinity of this integral exists. And also that means for big enough s, this guy goes to 0. So we'll just say for big enough s, the following holds. And so we say, so we're going to have 0, we're going to have minus f at 0 plus s times the integral from 0 to infinity of f of t e to the minus st dt. And ultimately this gives us s times capital F for the Laplace transform of s minus f of 0. Okay, good. All right, so that's what we wanted. We have the Laplace transform of f prime turns into s times the Laplace transform of f minus f of 0. So this is something that's really cool. Is basically the Laplace transform, and this is one of the really handy things about it, and this is what allows all of the algebraic techniques that we're going to be doing to happen, is it converts derivatives into multiplication by s. And that is the entire reason why we want to use this for differential equations. Okay, so let's go ahead and take a look at what we can do with this. So let's say I want to figure out what the Laplace transform of cosine of t is. All right, or say cosine of bt. Well, I know that cosine of bt is the derivative with respect to t of sine of bt, but then divided by b, because we'd pop out a b out of the chain rule. So we know what we can use. 1 over b is the Laplace transform of, so you can pull 1 over b out just because it's constant, and we have the linearity property. And now we have this. Now, if I want to take a Laplace transform of sine, we can just write this on the side here. We have a Laplace transform of sine of bt. Remember, that's equal to b over s squared plus b squared. So now I can go ahead and I can write 1 over b, and times, now using this last property, s times b over s squared plus b squared. And now I can cancel the b's, and I'm left with s over s squared plus b squared. And that's the Laplace transform of cosine of bt now from our table. Okay, so now we can get that last bit from our table that we haven't talked about yet, and that is the Laplace transform of e to the at cosine of bt, and that's going to be s minus a divided by s minus a squared plus b squared, and that's just by the shifting property of e to the at. Okay, so now we've just built up the entirety of table 7.2, and we did that by using these properties. So let's go back and review what these properties were. So the first property we had was linearity. So linearity basically says that L of a f of t plus b f of t at s is equal to a Laplace transform of f of t at s plus b times the Laplace transform of g of t at s. Okay, now we have the shifting property, and what do we get? So we get Laplace transform of e to the at of f of t, value at s is the same as the Laplace transform of f at s minus a. The next one we had was, we had the derivative with respect to s. And so we'll generalize that now. So it's dn by ds to the n of the Laplace transform of f is equal to -1 to the n Laplace transform of t to the n times f. All right, so now we also have the derivative on the inside. So that's when we take the Laplace transform of f prime. And if I go ahead and change that from just being prime to the nth derivative at t at s, then what do I end up getting? Well, I get s to the n times the Laplace transform of f at s minus s to the n minus 1 times f at 0, and then minus s to the n minus 2 at f prime at 0, and etc., all the way until we get to f to the n minus 1 derivative at 0. So this is just extrapolating upwards from what we did with just 1. You can do this, say, one at a time if you want, and just keep iterating that first formula we worked out. But keep in mind, this also requires that fn of t is of exponential order. Okay, let me see. So I think that is all of the properties we talked about. Yeah, and that's what we wanted. So these are the main properties of Laplace transform, and with them we generated the entire table of out of section 7.2. All right, so I'm going to leave it there, and yeah, we'll just head back to my face. Hey, so finally found the time to actually record that. So we went over the properties of the Laplace transform and actually went ahead and just built up the whole table from just one or two little examples that we worked out by hand. And yeah, I don't know how it has been for you guys, but I'm home taking care of my toddlers most of the time. I trade off with my wife every few days. But yeah, it's really hard to get work done. I can't imagine how it must be for a lot of you who might also be taking care of kids at home or taking care of family or just generally trying to switch to this whole online thing suddenly. Nobody asked for this, and I'm just trying to make it as easy as possible for you guys. Oh, hey, buddy. You trying to get the light? It's a pretty cool light, huh? Yeah, you like that? Anyway, yeah. So I hope you all are doing well and staying healthy. One thing I've learned around the babies is that there's two phrases you can't say. You can't say baby shark, and you can't say let it go, because that leads to a whole lot of wrong business. If you're watching this with your kids at home, I am sorry for what I just did. Here's a couple links, either in the description or up here, I don't even know, where you can satisfy your kids' itch for those respective songs. I can't tell you how many times I've sung Let It Go to my kids this time, this quarantine. Anyway, I hope you're doing well, and stay healthy, and we'll continue next time with the inverse Laplace transform. Okay, everybody just wants a light. Yeah, aren't you a cool kid? Look at you and your glasses.
Ooh,
Yeah.
it's this.
Yeah, it's a light. Look at that. Okay. All right, take care.